which are W map allowed, and what Planck should be able to do. And you see the reduction in range. And in particular, what is spectacular now is what are really having to do with inflation, or essentially initial condition parameters at this time. And you sort of see the kind of reduction that we can have, and we hope that finally we'll be able to start, clearing a little bit the inflation jungle. Now, how Planck fares as compared to a perfect experiment? Well, you can have an idea there, and it was designed to extract all of the CMB, all the temperature information. So what you see in essence is what is left after Planck if we were to do the same thing for polarization, that is having a cosmic variance limited experiment for polarization, which Planck is not, and which might be, the rationale for a fourth generation satellite to which maybe India will participate. Now, here is the status of where we stand concerning R, the tensor to scalar ratio, versus NS. And we are here. We know that there are broad categories of, say, inflation variance. And here is where we hope to be with Planck in a short while. So that's that's one way to go clear the ground. Another way is to sort of see how Planck X will do. And here is where we stand as of now when we, for instance, introduce neutrinos and say, well, neutrinos we're pretty convinced that they are there, so we should fit for them, right? We shouldn't assume that they are zero just because we don't see any signal. Of course, as soon as you do this, you increase the error bars. So here is the current status, and as well as W. Okay, this is a standard thing. And now the forecast for Planck using alone first, how this will reduce the error bars as compared to the current situation, and you see that this is essentially a factor of 5. Of course, on W, Planck alone, I mean, it's a low Z physics, so you cannot, CMB alone is not good at it, so you need to supplement it. And NS will improve by a factor of 2. Now, if you think that you do the same thing that for today, well, here is essentially what you can sort of expect to see. That is, you will not improve things that much by throwing in the large-scale structure stuff. Well, this is excellent. It means that we are already, doing what is already done at this time by combining CMB plus LSS. Of course, by then, LSF will have improved. So we might actually do even better than that. Now, just an illustration of what the isocurvature modes do to you. Okay, here is a sort of six parameter model, and what map can do with temperature and polarization. That was sort of forecast well before now, but this is just illustrating the point. And then you can throw in various types of isocurvature modes, and here is how this is degraded. So, of course, they are not very well determined. Okay, we know that. But of course, fitting for adding them in the fit increase tremendously the error bars. So it might be, this is the real situation we are in. That is, when we allow with a bit less theoretical prior, well, the determination might be actually of the parameters might be substantially different from what we say currently. Now, with Planck, you have a lot more constraining power, and you sort of see now, you can sort of compare that in essence, you get back to the situation, you actually improve on the current situation, even including those modes. So that's why we're going to the pain of going through measuring all of these extra modes in the tail, where you were seeing some small error bars, and say, well, I have the basic shape there. Why should I care? Well, that's part of the reason. And just to, I just multiply them so that you have an idea of the reduction of the phase space volume, and you go from 10 minus 11 to 0 information to 10 minus 24. So that gives you some idea of the reduction factor in this multidimensional space. Now I want to sort of illustrate another effect that we hope to be measuring, and which is very well known. The microwave photons are actually traveling to us through large-scale structures, the developing large-scale structures. And so there will be an effect, of course, that has been known also and has been calculated by theorists a long time ago. So let me just show you what is the effect first. Oops, sorry. Oops, back. Okay, so here you see essentially a lensed versus unlensed portion of map. And that's very simple because in essence you are taking microwave background photons. You have the bumps of, say, clusters and so on along the way. You have a number of them. And so what you have is gravitational light deflection along the path. So you're essentially blurring the initial image by shifting around the previous image. So this is a local deformation, you can think of it, and there is essentially a deflection field that can be derived from a potential, and this potential is of course related to the projected gravitational potential, and then also a kernel that is weighting the geometry, so you can learn essentially also about essentially the lossy part of the lensing, that is to say, things like W. So, so the first effect of lensing, which I just described, is essentially smoothing and moving power around, and this has been also computed a long time ago, and this is, well, not a little bit less long than what we were talking about. And by doing that also, this moving around the image, you'll realize that if we take a strictly Gaussian field, you'll create some non-Gaussianities, right? And in particular, you will create some 4-point functions. And you can actually, you will be able to use these various deformations, which are very well understood, to actually try to go and extract that signal. And of course, in the process, it generates B modes. And these B modes that are there, they are covering the sort of primordial gravitational wave background signature. And we know the amplitude of that. That's essentially 5 micro-K arc min. So it's not a very big signal. You imagine that you are now having an arc min, not a degree, now an arc min, and you have a 5 micro-K worth of signal, okay, per arc min pixel. It's tiny. Now, well, the story there is that, yes, we're starting to measure with the CMB the lensing deflection. So that was done first and not so long ago, in 2007. There was the first detection by cross-correlating with a low redshift tracer. Okay, so you have something that tells you, well, essentially, I suppose that this is a tracer of the potential well. So by having this tracer, which is correlated with the potential well, now I can look at the signature of the CMB that is imprinted, right, just along the way. And these were the first detection in cross-correlation. Now, what the big next step was done in 2010 by a direct internal detection, and this is not the direct on B modes, but this was the smoothing effect on the CMB. Okay. Now, that was one thing, and then now, and you can sort of see how this is done. I mean, you sort of assume that you have the theory calculation, yeah, and well, I will, anyway, that has been done. And now here is the situation for the lensing potential reconstruction. That is, and it's pretty much the current situation, and that's where we hope to be with Planck in essentially a year from now. In essence, that contains quite a bit of the Planck properties. This is a power spectrum of essentially the deflection field, okay? Okay, so, and that is directly telling you things about, you know, with the lossy universe. And so that can be helped to actually break the degeneracies on CMB alone. So you can think of this as a Planck alone, but now the reduction, when you look at these parameters, but you include the lensing information, you go from these dotted lines here to the contours there. So you actually lift some of the degeneracies which are from CMB alone. And I'm just doing a blow up here, which we'll hope to be accomplishing even with the CMB alone experiment. And expectations for Planck in terms of other detections, there are all kinds of that we can do, in particular ISW lensing. I put for you a collection of the anticipations, or I hope, provided we are able to tame all of these nasty practical effects. Now, there are more things in heaven and earth than 2 points correlation functions. And so we can write the probability distribution of the various harmonic coefficients, which are essentially the transform of the temperature field. Okay, and it's essentially a Gaussian term that you recognize here, and this is essentially the power spectrum -1. Plus, of course, if there are deviations from Gaussianities, the next order terms, which are 3-point, 4-point, and so on. The beauty of it is, in the simplest thing, the harmonic coefficients are directly related to the curvature perturbation, say, at the time of inflation, up to growth factors which are computed in a linear theory. So in other words, we know very well that if we have constrained well enough the cosmological parameters to get that function, we have a direct mapping between the harmonic coefficients and the phi. And so, of course, it means that when we're measuring the two-point function, we're saying things about the two-point function of the primordial field. That's what I've been telling you so far for quite a while. But of course, if you do this at the 3-point, you also have the same information now about the primordial 3-point. Okay, and then so in essence, we can have some information on this function f of k1, k3, k2, k3. Of course, there are many ways to arrange 3 points, as you all know. And the way they are arranged, that is a contribution to f, okay, is actually produced differently by different underlying physics, or by different inflation variants, if you wish. And so we started to do a little bit of classification there again, where it was found that essentially there are a number of broad classes like the local type, which can be obtained by a local deformation where phi is essentially the linear phi plus a phi square term, plus other configuration which all are sort of preferred by several classes of inflation, and I refer you to David Wong's talk tomorrow to actually get all of on this. The point is that there has been a lot of work on trying to relate specific models to specific values of the amplitude now for various shapes. And one of the things that is interesting is that a detection in the squeeze limit will essentially kill all single field inflation models, because given the value of NS that we know of, this should be very small. In other words, it should be undetectable. So if we measure them, it means that we have to have something a little bit odd. For people that want to be a bit more into this, I point you to 2 recent reviews on the subject. Now, one thing I want you to sort of take with is this is an already excluded value by WMAP of FNL, the amplitude of these 3 points of the local field, of 100. So here is the linear map, and here is the one with a gigantic FNL of 100 signal. So one way to take this is the frightening power of statistics. Say, I can't see anything. I've been asking to people several times, are you sure you didn't mix them? I mean, so anyway, so the conclusion is this is really frightening. Because of course we're essentially looking for a very specific signature in momentum space, right, or ALM space, and we're adding all of it to get a single number. So of course we reduce the error bars drastically. So you'd be better sure that there is nothing else polluted. You have to cope with the fact that there are foregrounds, the fact that noise is inhomogeneous, anisotropic, so you have to have a mask. So there are all kinds of technical issues about this. But they were essentially, in the course of the last 5 years, they have all been essentially lifted. And now we have essentially optimal estimators, which are unbiased minimum variance, and we know how to correct ones, and I just wrote them. That is, for a particular shape of the 3-point function that you are looking at, you can estimate an optimal amplitude estimator by doing this contraction with the estimating 3-point function. So the recipe there. It can be corrected for biases, and we have the practical way to do this by now. So of course, this is a story. Yeah, I'm getting there. The answer there is essentially this is 2 sigma of 42 uncertainty on FNL. So that's what I was telling you. The signal of 100 is already excluded by now. So how Planck will do? Well, I don't know, but suddenly we have made some forecast of this, and here is what Planck is expected to do as a function of the largest L mode that we can incorporate, in other words, the smallest scale. And in essence, you see that the limit is around 3 for delta FNL at 1 sigma. WMAP is 20. And you can sort of see that the perfect experiment could go all the way to 1. Perfect meaning cosmic variance using every single mode, including polarization. And the reason why Planck fails, quote unquote, is that we are not going all the way in polarization, which we know. But in temperature, we will essentially extract all the non-Gaussian signal. And this is true also for the local form, for the equilateral, and so on. You can also look at similar plots. Let me just move on. I just want to remind you that Cramer-Rao bounds are just bounds. Okay, so you are guaranteed not to do as well. you might be close. One of the sources of bispectra are the ISW cross-lensing, which is just one source, which would bias FNL by a value of about 1 if it was not accounted for in the analysis. We have second order effect at the last scattering surface, which is essentially weakly nonlinear evolution from, say, inflation time to the last scattering surface. So these can be computed. It's hard. This is essentially on the forefront of what is being done. It's anticipated that this is of the order of 5, but we don't have yet a full template to actually go after this. So I can talk to you on the side on this if you're interested. Of course, there are the astrophysical foregrounds. There is a poster outside by Lacasse et al. That gives an estimate of what would be the contribution from point sources, even after you've masked. And then this would be a negative bias of FNL local of the order of -6. So you see, I mean, when you are getting in the 10-ish range, I mean, you have to be extra super careful. And of course, you have all the instrumental imperfection. Well, when I'm not on the beach, that's what we're all busy doing. Actually, we've developed some alternative way of looking at things, which are model expansions, which are not specific to one particular model and so on. So that's sort of research that has been prompted by the Planck collaboration work. You don't have to look at the detail. The point is you can do this also at the 4-point level. Okay, then you can parameterize. You can build potentially optimal estimators. None has been done so far because the calculation is so horrible computer-wise, but we are moving in that direction. We can do similar things, of course, instead of going at bi and tri-spectrum, we can go at Minkowski functionals, which are just another way of looking at this. But these are some reweighting of the same objects, right? I mean, because this is the same information, but you're looking at the various part of the configuration and giving them different weights. This is also done with wavelets and so on. And currently, we're trying to do all of them because the different weightings are actually, it means the weighting, you're weighting differently the various systematics. Okay, so they are not as optimal, okay, but they are revealing of different artifacts. Let me skip that. I won't. Just want to say that Planck is not the end of the story. We already are proposing, well, that was a year ago, the next generation satellite, which the idea is actually to try to do for polarization what Planck is doing for temperature, which is essentially clean the ground and much larger number of frequencies, about 10 times the sensitivity. You can have an idea on the NSR, which we could be the contours if we were to use all of the information. Here is a comparison, what you will do on lensing. Same, comparing Planck and core, essentially. So immediately the payoff are neutrino masses, as an example. Now, conclusions. Okay, plain vanilla lambda CDM still offer a good fit to all existing data. We have percent values, and this is using the minimal model and throwing everything at it. And there is no compelling indication of deviation. We want better experiments, and some are around the corner. The search for extension, which is from Komatsu et al., you can sort of see there. I mean, the short story is there are none. So Planck essentially starts from this lack of surprises and detection. And in terms of conclusion concerning Planck, Planck works very well. I think well, you can read the detail, but I think what I want to take you home, and in particular the younger people to whom I'm talking, is that Planck plus AgPol plus SPT-Pol plus the newest generation like of LSS like DES, all of this will provide an amazing data set to play with. And so some of the complexities that I didn't have to cover that Dick showed you and pretended that I will cover are wide open, and we will be able to do that. So I think the coming years will continue for the CMB to be fantastic. Here, as I say that this was also, it's not me. Well, here's, for instance, the Planck pre-launch status. There are 500 names there. And then plus all the people that are now joined and will use it. That's, we're well in the thousands that Dick was talking about here. And here is what made Planck possible. Thank you.
Thanks, Francois. Time for few questions. The back? Yeah. Aditya, go ahead.
What does a positive FNL imply?
Where are you? Where are you? I take my card, talk to David tomorrow. You know, we can answer, no, I just don't want to. You know that you have, I can still say a few words. That first depends on which FNL. I mean, if it's a local or equilateral or whatever. So, I mean, we are entering the full phenomenology, okay, and it depends if you find zero for the others and so on. So I think that's why I thought of triplet. And this is essentially a new parameter space, okay, and we are right now trying to see which part of the jungle is most affected. And this is still happening. I mean, no, not yesterday. No, the day before, there was a full session on this. And some new model keep popping up. So what we can say is for this particular model, what this says, I mean, of course. So, I mean, I'm sorry not to be more precise than that.
Comment on the
What do you want me to comment on B modes?
Is it going to better your chord bounds?
Well, what I did say, there were two type of upper limits so far on R. One which are the indirect ones using the temperature and T, TE, and EE data. And from there, the constraint these are the best constraints we have so far, which are of the order of 0.2. Okay, then this is in the details are in the slides. But if we go to actually go straight forward, that is say, let's look what the upper limits on the B mode are telling us, not indirectly, just power spectra of the B mode part, it's more like 0.7. And this is the BICEP experiment, which was targeted explicitly to do this by looking at the sort of intermediate scale. Okay.
So I was curious whether you'd be able to discriminate between FNL positive or negative.
Yeah.
For sure, independent of...
Of course,
okay.
I mean, you know, there is no discrimination there against sign.
Okay.
It's simply that the signature, I mean, you can actually, we do even have the simulations because, of course, I mean, you can also see what are the effect of the various signs and so on. I mean, it's just a change of weight and so on. It's actually one of the interesting byproducts of Planck is, in particular in Europe, was that, well, in the process, a lot of things we had to start to, well, you know, invent the various technologies, simulations, and so on. And I can only wish that, you know, India started to join the fun. It's pretty obvious on the theory side, and I can only hope that this will also be true on the hardware side in the, you know, in the next iteration to parallel the previous feature.
I mean, I'm curious about the sign because, you know, there are other alternate probes. Like if you look at the abundance of strong lensing arcs in lensing.
Yep. Yep.
You can, especially for the 3-point function.
Yeah, and that's going to be part of the extension.
Right.
Yeah. So, sir, here.
Oh, yes.
So for FNL again, will you also be doing an independent analysis of the SZ detected clusters from Planck?
I'm not sure that this is the most sensitive probe that we can
No,
have.
it's not.
Yes, first, for a fact, I don't know. Okay, that's the first part. But SZ, we are doing what the other experiments can't do, which is just a very large scale. And I don't know when you have that particular selection function, if you wish, whether we are sensitive at all.
SPT did an analysis recently, so I was wondering if something similar will be possible.
I think what we will do is we will do co-analysis again. I mean, I think that will be the way of the future.
One last question.
This is regarding FNL again. With
Oh, David, you're going to have some work. I mean, I have guaranteed questions for you. Yes.
My question is to do with data, not theory. So the blue map data, if you use the bispectrum, FNL seems to be preferred value should be positive. Whereas if you use Minkowski functionals, the preferred value seems to be negative. So would you say that the local type FNL is not really what is the present in the primordial form? Or is it foregrounds, or is it something else?
Well, if I knew, I would already have written up. Well, let's focus on the local form. Yes, we are indeed. I think that part of the light will come in making sure that the various indicators are consistent with each other, because we do have now essentially all the, well, at least at the 3-point level, not the 4-point. We have all of the sort of theoretical technology in place to essentially relate whatever F form that you have to, well, skewness coefficient, which are those that enter the Minkowski functionals, or in a similar fashion, the B's and that enter the straight detection of FNL. So I think we are all ready to sort of see whether we you know, the two indicators which are different, we have a different sensitivity on instrumental systematics, of course, because you're doing a different weighting, right, are consistent or not. And that, well, we're just doing it. Now one thing that we're facing with Planck, and where I think we will not be done with it by the time the data goes out, okay, is the full use of the frequency information we have. It's what people have been doing mostly have been essentially either ignore, I mean, just do a mask of the sky, say where there is a foreground minimum, and you know, just say, well, how things vary when you vary the mask. Okay, that's one thing. In our case, it would be take at 143 gigahertz and throw all out. Or you do some kinds of cleaning, okay, but this is very hard to actually do a formal propagation of errors, okay, all the way to say something like FNL. I think this is fair to say that well, nobody has done this so far properly.
Okay, I think we are coming to the end of the session.
There is this guy that wanted to say something.
So let's end the session. So thanks, Francois and Singh. There is some announcement by...
Please assemble for the conference group photo in the lawns just outside.
Will be Masaru Shibata on coalescence of binary neutron stars and black hole neutron binaries, neutron star binaries. So we'll begin with Raphael Sorkin.
Feels more comfortable. Yeah. First 4,096 elements of the beginning of the universe, or what would be equivalent for this particular dynamics. It could be a record of the first 4,096 bursts of new causal set elements at the start of a new cosmic cycle of expansion. I am, of course, not claiming that that's actually what it is, but it's nevertheless, I think, a quite pretty picture to look at, and it gives you some sense of what a causal set is like. Over there on the, if you can see it on the whiteboard, is a much simpler, smaller causal set. It gives you the basic idea of what it is. Here's the title that Sumati mentioned, and here's some of the people that the work I'm going to report on was done with and by. These are people involved in the recent two main advances, major advances in causal set theory, which is what I'll be getting to in the second part of the talk. If you're interested in some references, if you want to follow up further, I direct you to the Perimeter Institute Recorded Seminar Archive, or PIRSA, website, where there is the first reference, you could see this hand, right, if I use this as a pointer? Okay, so the first one is a mini course that was given by me and Faye Dowker last year. The second is a short introduction to the mini course by Joe Henson. And the third, which is currently is a lecture, a public lecture given part of the public lecture series at Perimeter by Faye Dowker. It's currently in the hands of the TV station that covers these, but when it, I don't know why this keeps moving, when it's returned by them, it'll also appear on the same Perimeter Institute website. So I had originally intended to try and give a little background just on quantum gravity in general and say a few words. I'll still say a few, but in order to finish on time, there'll be even fewer than I had originally intended. But I wanted to try and situate the causal set theory within the context of quantum gravity in general. among the different ideas that are put forward in the search for such a theory of quantum gravity, I think the causal set hypothesis is distinguished by two features. First of all, its logical simplicity. You can see what a simple thing a causal set is, at least in that whiteboard picture. And secondly, by the fact that it incorporates the assumption of discreteness from the very beginning. In fact, causal sets theory is really nothing more than a blend of the idea that causality is the basic structure of space-time, the one that reflects a deeper structure, and the idea that this deeper structure is discrete. So some of the questions that causal set theory addresses, and that any quantum theory of gravity needs to address, at least some of these, I've listed here, and I'll just, as I said, touch on a few of them. The first, and in some sense, I think the most basic question is, what is the deep structure of space-time? Is it continuous? The more conservative option, is it discrete, or perhaps something else? If it is discrete, what kind of discreteness are we talking about? Is it a very ordered kind of discreteness like you find in a diamond or a salt crystal? Or is it some sort of disordered discreteness of the sort that you find in a fluid whose molecules are distributed more or less at random within space? Once we answer, or once someone settles on an answer of what is the deep structure, the next question, of course, is what are the deep laws of motion? In other words, the dynamics of that structure. The answer that causal sets gives is fairly definite, no to some possibilities, like the Schrödinger equation, and the kind of dynamics that it seems to require is something more of the nature of a path integral. More precisely, it's something that's expressed in terms of what people sometimes call a decoherence functional, which is a sum over paths, in this case a sum over causal sets, but not over individual ones, but over pairs of causal sets in the manner that is used in the Schwinger-Keldysh formulation of, for example, thermal field theory, if you happen to be familiar with that. The main point I want to get across is that you need some space-time formulation, which was actually what Feynman called his first paper on path integral, as opposed to a canonical or spatial formulation. And that there are further small modifications where you have to work with a decoherence functional and not something like an S matrix. There's some related theoretical questions, sort of subsidiary to these two. The only one I'll highlight here is the question of what are the quote-unquote observables of quantum gravity. This is in a broader sense what people sometimes call the problem of time. In the continuum, it manifests itself as the question, how can we talk about diffeomorphism in variant quantities when our theories are usually set up to describe local quantities which are not diffeomorphism invariant. The same thing shows up, I think, in all formulations, and in the case of causal sets, it's an issue of label invariance, not diffeomorphism invariance. The reason I stress this one is because I think we can claim to have a complete solution of it within the context of causal sets. Then finally, having discussed what you might call the kinematical questions, the dynamical questions, of course, the most important, somewhere down the line, are the phenomenological questions, of which maybe I'll stress just two. If you can read fast enough, you can have a look at some of the others while I'm talking. The first one has been much discussed here. Why is the cosmological constant so small without actually being zero? The last one that I want to mention down here is initial conditions for the cosmos. If we're optimistic, we can hope that quantum gravity is what's providing the initial conditions for the Big Bang, and not something like inflation. And in that case, we would get a tremendous amount of insight, observational insight into quantum gravity theory from all the cosmological data. Then if we entertain that hope, the question we have to answer can be posed in the following way. why, which just comes from extrapolating what we have now using the Einstein equations back to the Planck time, you find that at the Planck time you would have something like a Planckian density, but what you find that's strange, this is this large number problem, is that this radius or the diameter of the universe is far, far more than the Planck density. Let me also go back to the other question about why is the cosmological constant so small without being zero. I want to try to make a point that would take a little longer to make in detail, but let me at least claim that in a discrete theory we have two problems that merge into one. The cosmological problem is, constant problem is always there, but there's also the question, why do we get a continuum at all? Why does this discrete structure manage to stretch itself out and behave something like a manifold and not by some completely tangled up thing that has nothing to do with the manifold? I want to say that these are essentially the same problem, and because they are, it might be that the right way of getting a handle on the cosmological constant problem is to think of it in this other way, as the continuum problem, or the problem of getting space-time out of the underlying discrete structure. Okay, so what does causal set have to say, causal set theory have to say as an answer to some of these questions? Or more generally, where does causal set theory stand now? What is the status of the program? I had talked before about kinematics, about dynamics, and about phenomenology, so let me take things in that order. The question of kinematics from the point of view of the causal set is the question basically of how can something like a manifold, even in principle, emerge from some sort of very rudimentary structure which is just an order relation among discrete elements. I'll say something more in detail about how that takes place, but at this point let me just say that I think that's pretty well under control. We have a good understanding of how it can happen. That's really the origin of the theory, but we also have an understanding in detail how to read out the geometrical information from the order theoretic information. So there are ways, if someone gave you a causal set that was well approximated by a space-time manifold, a Lorentzian manifold, we have more than one way of knowing the dimension of that manifold. The Myrheim-Meyer dimension, it's called, is maybe the best one. We can talk about geometric quantities like length. In fact, length is just the most obvious transposition to the causal set of the continuum rule that the distance between two time-like related points is the length of the longest geodesic. Here we have the length of the longest causal chain of elements. And I don't know why this. Okay, so length. We also have approximate notions of space-like hypersurface and of homology, topology. We know how to read that out. And the thing I mentioned before, I don't know how to. The so-called problem of time is solved. That is, we have a complete set of observables called what are called stem events or stem predicates, in terms of which any meaningful question, any covariant question, can be built up by logical combination. So I would say that in essence the problem of time is no longer a problem for causal sets. Turning to dynamics, there's really two prongs to this question, what I've called dynamics in a causal set and dynamics of the causal set. The second is, of course, the more important one, because that is actually quantum gravity. But especially from the point of view of phenomenology, the first one is also very important. How would you write down equations describing the propagation of matter or fields in a causal set? In other words, how would you do the analog in the causal set of quantum field theory in curved space-time? Here I'll mention two questions. One just about classical evolution of a scalar field, so that we could study, for example, the effect of propagation of light over long distances in the cosmos. And could there be any indications of discreteness, signals of discreteness coming out of those things as has been suggested. Second of all, we would of course want to do quantum field theory, and we now know these are two of the advances that I referred to in the beginning. We now know how to do both of those things. The second thing, which arose actually from asking those same two questions, is that we now know, well, so how would we describe the dynamics of a causal set? For a long time we've had a classical stochastic dynamics called the dynamics of sequential growth, but I don't know, is there some way that I can, no, what I'm trying to do is move this hand around to use it as a pointer, but every time I move it, yes, I know, I'm trying to do it gently, but yeah, maybe I should do it this way, yeah, okay. Okay, so okay, and then this. Okay, so getting to the dynamics of the causal set itself, we've had for a while a classical dynamics of sequential growth, as it's called, which represents the dynamics as what's known in probability theory as a growth process, or a burst process, I should say. However, so far that has not given rise to a quantum analog, unfortunately. But in its place we have something else, which is a kind of action functional. We now know how to write down something which represents the continuum, the discrete counterpart of the continuum Einstein-Hilbert action on a causal set. And this, although it's not local, because nothing can be strictly local in a causal set, as I'll emphasize later, due to the radical non-locality of the structure, nevertheless it's pretty close to local, it's bilocal. And when we apply it in 2 dimensions, we actually, turns out we don't even have to worry about the action itself. There's a kinematic restriction to 2-dimensionality, and when we impose that, just entropic effects already produce a manifold. That is to say, if we pick a 2-dimensional causal set perfectly at random with a high probability, it looks like a space-time and actually like a flat space-time, a portion of 2-dimensional Minkowski space. What? Oh no, this is fine. This is fine. Thanks. However, when we come to more realistic things, like 4 dimensions, then the action will certainly play a role. And I can say just at this point that Monte Carlo simulations are just beginning to be done with this new action functional that we have. So let's come finally to the phenomenological questions. I already stressed about lambda. Have I gone backwards? There we go. Okay. So the early success there, which was a very great stimulus to those of us working on causal sets, when it seemed to come true, was the prediction of fluctuations in the cosmological constant. In fact, the prediction was either in or just shortly after the very first GOA conference that was held here in this series. It predicted a cosmological constant of this order of magnitude of an unknown sign, because one is dealing with fluctuations. So for those who know something about baseball terminology, I used to say that quantum gravity is batting 1,000, which means a perfect record. But someone in the sense that quantum gravity has made only one prediction and it came true. On the other hand, a friend of mine pointed out that people also predicted from quantum gravity that the cosmological constant had to be exactly 0, or very nearly so. And so maybe I can say it's batting 500. The other issue I stressed about, the question I stressed about setting initial conditions for the universe, there I could say only something in the nature of just something qualitative that comes out of a toy model and can't be really taken fully seriously, but it indicates the way things might go. So this classical sequential growth that I talked about before gives rise to something, a kind of what I call a Tolman-Boltzmann universe, which is a kind of cyclic universe in which it starts at Planck size, expands, recontracts, and so on. Each time the expansion is bigger, and if you wait long enough, it'll be a very, very large and homogeneous expansion, and so it'll give rise to something rather like, just as by way of analogy, what we really need for the early universe. So it's a kind of hint as how a kind of answer that might come out of a more complete quantum dynamics. Another thing that perhaps has a chance of being observed would be some effect of the underlying discreteness on the propagation of particles and waves in the underlying causal set. Everyone is familiar with the fact that the atomic structure of matter, not of space-time, manifests itself in Brownian motion and this kind of fluctuating motions. The same thing arguably should happen in the causal set, so that even a particle moving in a vacuum would undergo some sort of Brownian motion, whose elements represent other causal sets. So if you can see, if you're close enough to see these little ones, you'll see a large number of pictures of small causal sets. This is what's called a Hasa diagram. And it's just a graph that shows the order relations among the elements of the causal set. What a causal set is precisely a set of elements which have the same kind of order relation that space-time itself has, which is what's called the partial order. That is, some elements are to the past of other elements, like these two. This is to the past of this. You can also think of this as being an ancestor of this. It's another way of referring to the same relation, but it's this fundamental temporal relation that defines the structure of the causal set. And it's transitive, so if this is to the past of this, and this one is to the past of this one, then of course this one is to the past of this one. But we don't bother to draw in that line because it's implied by the ones that are always drawn in, and it would just clutter the diagram. So if you use the minimal set of lines, you produce a graph which is called the Hasa diagram. But that's all a causal set is. It's just a partial order. It's called partial order, partial, because not every two elements are related, just as in space-time. They can be space-like to each other, like these two, or they can be time-like. There's also the concept of link, which is just basically one of the lines in this graph. It's the causal version of the nearest neighbor relation, if there is an analog of the nearest neighbor relation in a kind of crystal lattice or random lattice. But it's spatiotemporal, it's causal, not simply spatial, and that makes a huge difference. So you might ask, given this, well, this is very pretty maybe, but it's very, very simple. What has it got to do with space-time? How can a space-time emerge from some sort of set of elements with only this causal relationship among them? The answer is represented, or is epitomized by this slogan. We're looking for geometry, we have order, and we have discreteness so we can count. And the slogan is that geometry is order plus number. More specifically, the order of the elements is reflected in the causal order of space-time, its light cone structure, if you will. And the number is what gives us the missing information, the volume information about regions of space-time. Here's the same slogan again. Let me say a little bit more about this, because there's a crucial element which tells us the answer to the question I raised earlier of whether the order had to be crystal-like or fluid-like. And the answer seems to be, in order to do justice to this hypothesis that the volume of a region of space-time is a direct reflection of the number of causal sets, elements composing that region, we need to think of the elements of the causal set as if they were randomly distributed by a Poisson process, in fact, in the space-time. This is the only way we know to get this number volume information to be generally true. The reason that this comes about, and you might think, why is it so hard to get this uniform distribution? And you might think that fluid, I draw a little sphere around it, I count the number of molecules in there, I divide by the volume. and that's the density. It doesn't much matter how big the sphere is as long as it's not too small and not too big. Why can't we do something similar to define continuum quantities in the causal set? The answer is that the sphere in the Lorentzian signature is a very different thing from a sphere in the Euclidean signature. A Euclidean sphere is a little compact bounded thing, whereas a Lorentzian thing is something that stretches out arbitrarily far along the light cone and doesn't in the same sense give you local information. This is what I was referring to as the radical non-locality of the causal set. It's overcome precisely by this idea of sprinkling. So, or more precisely, Poisson process. So what we say, we use that to give a criterion for when a continuum spacetime, a manifold, is a good approximation to a causal set C. And the criterion is in terms of what we call faithful embedding. The manifold is a good approximation to the causal set if you could find within the manifold an image of the elements of the causal set, an embedding of the causal set into the manifold, which preserves the order relation and is uniformly distributed with density 1. So the causal set should be as if it was created by a Poisson sprinkling of the space-time. Now, a very important feature of the Poisson process is that it respects Lorentz symmetry, and it respects it in a very strong manner. And here's a theorem that actually says that in a precise way. But let me say informally what's going on with this theorem. The causal set, a Poisson sprinkling is a random process, and so one has to distinguish between the process and an individual realization of the process. For example, think of a roulette game. The process is circularly symmetric, you throw the ball, but the individual realization is not. The ball ends up in one particular angle. Poisson sprinklings are not like that. Not only is the process Lorentz invariant, but the individual realization is as well. And that's so it's virtually impossible to break Lorentz invariance using the kind of discreteness embodied in the causal set. What this theorem says in words is that if you do a sprinkling of Minkowski space, with probability 1, you will not prefer a particular frame. You will not break the Lorentz symmetry. Excuse me. No, in this theorem, n is infinite, so it's a sprinkling of the entire Minkowski space. And here's a picture just to illustrate why that's true, or to make it look plausible that that is true. Here we have a sprinkling of Minkowski, a little portion of two-dimensional Minkowski space. And here's a blow-up on the right, is a blow-up of a small region there. You can see it looks random. And below, on the lower left, we have the same sprinkling after subjection to a boost. So it's highly boosted, as you can see. And then we take a little square here, it happens to be the same coordinate values as the original, and blow it up. And I think you can see that although these are not in detail the same, there's no way you would be able to distinguish before from after. That is, the process of boost, even a very large boost, doesn't disrupt the uniformity, and therefore you don't you don't distinguish a frame, you don't prefer a frame. Another thing that comes out of this Poisson process is what I've called the radical non-locality a couple of times of the causal set. That the idea of nearest neighbor doesn't act the way you would expect. Instead of having a small handful of nearest neighbor, okay, I'll speed up. So instead of having a handful, you have an enormously large, if you had all of Minkowski space, an infinite number. And this picture illustrates why, because of the non-compactness of the Lorentz group. So if this were a nearest neighbor, a link, causal link, then boosting it should give you another possible one and another possible one and so on. And so the actual nearest neighbors will be spread out along the light cone in a way that makes it very hard to write down something like a discrete D'Alembert space of d dimensions. Let phi be a test field on this Minkowski space whose D'Alembertian we would like to be able to reproduce. That's just a list of numbers because the causal set is a discrete object. So here we have a what we're looking for, we can represent it as a column matrix, and what we're looking for is a column vector, I should have said. What we're looking for is a matrix which, when applied to that column vector, will give us the value of the D'Alembert at a given chosen element of the causal set. This is very difficult for the reason that I illustrated, that this diagram illustrates. If we just take all nearest neighbor contributions, we get a bunch of things which are not really close in the desired sense to the element where we're trying to reproduce the D'Alembertian. Nevertheless, so it requires some sort of miraculous cancellation. Nevertheless, that cancellation is possible. And here's the simplest version of how the matrix looks, appropriate to 1 plus 1 dimensional Minkowski space. So it has up to some overall scale factor that I've omitted. It has a minus 1/2 in the diagonal, and the off-diagonal elements depend only, so off-diagonal elements now refer to 2 elements of the causal set, and the number that you put there in that location in the matrix depends only on the number of causal set elements causally between the 2 elements to which the matrix element refers in such a way according to this function. So if that number is 0, we put a 1. In other words, if the 2 elements are actually linked causally, we put a 1. If there's 1 in between, we put a minus 2. If there's 2 in between, we put a 1, and otherwise we put a 0. And that turns out to do the trick. In 4 dimensions, this we knew for a while, but the new thing is we can now do this in any dimension, and there's a systematic way to write down these coefficients. You can see they're binomial coefficients here. Here there's a more disguised version of binomial coefficients. It's the same thing, but now we go out a little farther. We have 0 intermediate elements, 1, 2, and 3, with this particular set of coefficients. There's also a 1-parameter family of generalizations of this that take a more complicated form, but are perhaps necessary for certain practical purposes. That's given here. Let's ignore that for now and just stick with the simplest one. So what I told you was only for flat space. However, this expression that we have is formulated in order to make sense in any causal set. It just refers to the intrinsic structure of the causal set. And we can ask what happens when the causal set is well approximated by a curved space-time rather than a flat one. And what happens, instead of being just the D'Alembertian, it becomes corrected by a curvature term. Since it's a scalar, it sort of had to be a multiple of the Ricci scalar. And it's in fact minus 1/2 the Ricci scalar in even dimensions. In odd dimensions, you get a sign flip. That means 2 things. It means that we can write down a scalar field equation, a wave equation in a curved space-time by correcting for this R term. But more importantly, what it means is that we now have a way of getting access to the scalar curvature itself. If we apply this matrix, this operator, to the constant function, then this box term drops out, and we're left with just the scalar curvature, which is what we want, up to sign. If we add this up over the causal set elements, we get the discrete counterpart of the Einstein-Hilbert action. And if we ask what that action is, it's actually just a sum over certain special kinds of sub-causal sets of the large causal set, which are called intervals, order intervals. And you can think of them as roughly analogous to the simplexes that you sum over when you're doing Regge calculus, especially causal dynamical triangulations, or roughly analogous to the cells that one sums over in the spin formalism. But in this case, it's just combinatorial. We just have to count up the number of links, the number of 3 chains, here's the number of diamonds, and a couple of others, and add them all up with certain weights, and that's the action of the causal set, of that particular causal set. That raises a kind of embarrassment, which is now that we have the analog of the Einstein-Hilbert action, what do we actually use it for? And I want to stress, at least in my opinion, that this is a very crucial question for anyone thinking in the path integral terms about quantum gravity that goes well beyond causal set theory. We don't know, even in the continuum, even formally, I would claim, exactly how we're supposed to use the Einstein-Hilbert action in the path integral and what it's supposed to do for us. Some people think an S matrix type of thing. Some people think it's a projection operator onto solutions of the constraints. When you come to ask the decoherence functional, there's an ambiguity. There's another ambiguity that I don't have time to describe. I just want to sort of appeal or recommend to people to think about this problem, because it's something that anyone who's interested in path integral gravity can think about. So without thinking, however, we can just follow our nose and attempt Monte Carlo simulations analogous to those that have been done recently with great success in causal dynamical triangulations. And that's what's happening, what's starting to happen now. There's also a very intriguing connection to black hole entropy that we don't at all understand that seems to be coming out. In a way, it seems to be resonating with some of the suggestions that Padmanabhan has made about entropy being action, but in a way that's completely unclear at this point. But stay tuned for this. Then the last thing, the second that I wanted to talk about, was the other advance of causal set theory that's taken place, also coming from the scalar field investigations. In fact, it is a scalar field theory, a quantum field theory. I showed you before how you could write down a classical wave equation for a scalar field, but now we want to do a quantum field theory for a scalar field on a background causal set. So we fix the causal set. To set the stage, let's think about how we provide, how do we, excuse me, how do we formulate a scalar field theory in the continuum, say in flat space-time? So basically there are two inputs. You have a wave equation, and you have the commutation relation, and you have some notion of vacuum also, which comes from thinking about positive frequency. At least that's one way of saying it. And fortunately, these two inputs are consistent because the commutator function, this delta xy, which it turns out to be related to the retarded and advanced Green's function in such a way that when you apply the wave operator to it, you identically get 0, and that's necessary for consistency if you look at this equation. The sad news for the causal set is that we don't know how to do the same thing. We can find the retarded the Green's function and therefore the commutator function, but we don't know how to find an equation of motion that would be compatible with it. So what should we do? Well, it turns out that you can just forget about the equation of motion and build the whole theory from the commutator function. How can the commutator function just by itself yield the full operator algebra and even the vacuum state, which is what I'm claiming that it can? Well, the key is that it's a free theory and it's a Gaussian theory. We're looking for a kind of Gaussian vacuum, or what I would really call a Wickian vacuum, one in which Wick's rule holds. For those who work on, say, CMB fluctuations and are looking for non-Gaussianities, this is very familiar to you. People look for the 3-point function to not vanish, or they look for the 4-point function not to be related to the 2-point function in the simple way that Wick's rule tells us that it is. 0 minutes, okay. Okay, so the point I'm trying to make is that the whole theory is encapsulated just in this 2-point function, which is called the Whitman function in the context of field theory. So what we need to do is figure out how to reproduce the 2-point function, where starting from what we have, which is the commutator function, which is just obviously the antisymmetric part of the 2-point function. And there's a very simple prescription, amazingly, that does this for you, which tells you to just choose for the Whitman function the positive part of I times the commutator function. What do I mean by the positive part? Well, here it is in formulas. I know some of you can't see in the back, can't see down here. But it just says that you take the commutator function plus the absolute value of the commutator function, divide by 2. What it says more practically is you expand out an eigenfunction and you throw away all the terms in that expansion that correspond to negative eigenvalues. So this had nothing, notice that I never mentioned positive or negative frequency, but remarkably this prescription reproduces in Minkowski space exactly the same results that you get in a free field theory. So we did this without being ever asked to define positive frequency. And so as a byproduct, we get now a distinguished vacuum state, let's call it, for any, or ground state for any compact region of any spacetime, and many non-compact regions of spacetime. So all this was in the continuum, but if we recast the theory that way, now we can just carry everything over to the causal set straightforwardly. All we need is the retarded Green's function, and we do know it. I slightly understated the case here. We know it in 2 dimensions in full generality. In 4 dimensions, we know it for the flat case, for arbitrary mass squared, and in general, there's good suggestions that are not yet proven on how to find the Green's function. Well, there's a lot more to say. I'm already beyond 0. So, but if I had a little more time, I would say something about the decoherence functional. That is the history's formulation of this theory, which makes it possible then to include interactions about the classical limit, how it's related to the wave equation I showed you. But let me just finish by mentioning one other byproduct, which to me is extremely interesting, is that we now have a new formula for the entropy, in particular for entanglement entropy, expressed directly in terms of the Whitman function. So it's a space-time formula for entropy. Using that, we can now address the question of entanglement entropy in a black hole causal set. That is a causal set that represents a black hole. And we can go on and talk also, using the theory itself, talk about Hawking radiation. So that, I think, will be the next step that we'll try to take. Thank you.
Your idea about an ever-present lambda, in my view, is very attractive and powerful. But after your paper, there's a work by John Barrow saying that there are constraints coming from the microwave background which do not permit such an idea. I'd like to know if you see a way out of what Barrow said.
Well, I don't, the answer is I don't know how to address it properly. So the original prediction was just for an order of magnitude. Then we followed that up, this paper with Dodelson and so on, in which we made a more concrete model. But in order to, the idea of a cosmological constant, varying cosmological constant in the most straightforward form is not consistent, because if you write the Einstein equations and just let lambda be a function of x, then the Bianchi identities tell you that it has to be a constant. So one has to decide how to implement the idea of a varying cosmological constant. In our paper, we only were able to do that to a limited extent under the assumption of strict spatial homogeneity. And we mentioned in that spatial inhomogeneity was certainly a potential problem for the theory. And what John Barrow wrote, what he did was emphasize that fact, that if you had fluctuations of order 1 in the spatial wave, then you would mess up, the CMB, and it would not be viable. And so I think to address that, we need to understand the phenomenological, what we need is an extension of that phenomenological model to take into account arbitrary fluctuations and not restrict to spatial homogeneity, because if we restrict to spatial homogeneity, we also can't study the growth of structure and so on. So that, I think, is a very important thing that should be addressed.
I'd like to ask you to comment on the choice of sprinkling. You said that you choose Poisson because it has Lorentz symmetry. And do you still recover an algebra if you choose other? Is that a faithful choice, or?
Right, we don't know how unique that is. Actually, I said something stronger. I didn't just say that we chose it because it gives Lorentz symmetry. I said we chose it because it gives volume equals number. It gives, in a strong sense, a uniform distribution of points. And that once we choose it that way, we get Lorentz symmetry for free. Or we're forced, if you like, to accept Lorentz symmetry. So it's a very important question. Are there other forms of sprinkling, other distributions that lead to uniformity? And there's only a conjecture. That's all I can tell you. In fact, if someone is looking for an interesting problem in probability theory, point processes, there's a very simple conjecture that's not even settled. Is the Poisson process the only Poincare invariant one? Then beyond that, there's a more, that's asking for Poincare invariance. But then there's this conjecture that would capture what I was saying before, which is that either the Poisson process or something virtually equivalent to it is the only kind of process that achieves the degree of uniformity of distribution that the Poisson distribution process does achieve. And I could tell you later an exact formulation of the conjecture, but that's a very important question.
You wrote down a kind of a... You wrote down...
I can hear you, but I don't know.
So
I can repeat
you wrote down a formula for the action, but it was just Einstein-Hilbert action, and we know that that is not a good action because it needs surface terms. And so the question is, what is the situation with respect to that?
So that's also a good question. We don't understand the surface terms at all at this stage, I would say, except for some hints. You might have noticed that something went by very quickly that said there's a kind of Gauss-Bonnet theorem in the two-dimensional case. That gives a little bit of insight into the surface terms. But at this point, we don't understand what surface terms are captured by this action. That's another very important question.
You get Riemannian geometry when you make a transition from the discrete to the continuum. But why don't you get any other sort of...
also a very good question. Why don't, well, so it depends...
Torsion, for example.
Sorry?
Torsion, I mean, connections which have torsions.
Well, that we don't get because what we're getting is the metric. We're getting the light cone structure and the volume element, and that's closely connected to the metric. We're not getting a connection in any sense as a fundamental object. I would believe that it's not a fundamental object. And so the issue of torsion doesn't really arise. But one might raise another kind of question is, why don't you get a Finslerian type of geometry? For example, why don't you get square light cones instead of round light cones? That indeed, I think, is another very fundamental question that could have been asked in many approaches to quantum gravity. At this point, I don't have a good answer, except that I think the round light cones of Lorentzian signature, pseudo-Riemannian metrics, are somehow more, well, we know they are the most highly symmetric kind of light cone that you can have. And I would guess that that's actually the key to why nature chooses that. But could there be a small admixture of Finslerian? Maybe so, yeah.
You mentioned a couple of times scalar field. How do you define fields in this language? A scalar or vector? Or
Yeah, so that's another very good question, which I skipped over. It was there on the slide if you read very rapidly. So the scalar field is not hard to describe because it just means that you attach, to each element of the causal set, you attach a number. That's a scalar field. But as soon as you have something that has a bit of non-locality in its definition, no, I don't think so. What is a scalar field mathematically? It's a mapping from the manifold to the real numbers if it's a real scalar field. So it just attaches to every point of space-time a real number. Since we have here a discrete object to replace space-time, we can still attach to each element of the object at a real number. That's all I mean by when we come to something like a gauge field, then it's another whole question. And underlying that is the question that I also skipped over. Do we need it, or does it come out in some effective way from the structures we already have?
You mentioned that you solved the problem of time. I'm here.
Sorry, where?
It's me.
Yeah. Oh, there you are. Okay.
No, it doesn't work.
Yeah.
Well, you mentioned that you solved the problem of time in the Causal Set theory. Which problem of time did you solve?
Well, that's also, every question is really good. Would you like, some of you like to give the lecture instead of me? So there are many, indeed, it's better to say problems of time and not problem of time. And some of them are solved trivially theory and causal set theory. So one of the problems of time that people often refer to is in the context of canonical quantization, which is that there you deal with space and not with time. And so there's a problem of recovering time. That's not the problem. That's often what people mean when they say the problem of time. That's not the problem that we've solved because we're working with a sort of atomic version of space-time. Time is there as well as space. So that is solved in the most trivial way. But then there are more subtle problems of time, all of which stem in the continuum from the diffeomorphism invariance of the theory. That means that it's very hard to talk about an observable, some object that you could, for example, measure in a Monte Carlo simulation, or that represents a physical question, like what's the maximum radius of expansion of the cosmos, say it expands and recontracts. All these physical questions are very hard to translate into simple quantities about a diffeomorphism and invariant kind of structure. And that's the problem of time in the broader sense, and that's the one that we've solved. We've shown how to write down very simple quantities or very simple questions that you could ask about the causal set, which are basically the question of, could it have been labeled in such a way that the first n elements looked like this causal subset? Those have a clear physical meaning, and from those you can produce by logical combinations all other covariant questions. Okay, I've been cut off, so.
What I could suggest is that two questions be asked, so I can see two people here, but...
And I'll shut up?
Yeah, I'll the answer later.
Okay.
Okay. I'm here in the back at your left. I'd like to hear your point of view with respect to one sort of common, very general puzzlement that all your this approach raises, which is the following. You start from the discreteness of space or space-time as one of your main. Now, of course, the idea of discreteness in quantum gravity it's always there. It's very old in one way or the other, and it comes from the discreteness of quantum mechanics, of course. I mean, in quantum mechanics, we have learned that the world is discrete at small scale in various sense. However, the discreteness of quantum mechanics is the discreteness of the hydrogen atom, of a quantum oscillator, and so on and so forth, which is a more complicated sort of discreteness. It's just the idea that the world is made by little bits of something. The orbits of electrons are not. So I'm curious to know whether you see this, is that discreteness the discreteness of quantum mechanics, or you're assuming something else here?
I wish I could answer.